Hello?
Hello.
Hi.
Hi.
I'll just send the Muriel link. Just a second. Well, wrong thing. Back to YouTube. Here. This is the link.
Mm.
So I think I want to practice some questions from Chapter 3 problem set that I sent in another email like a while ago.
Okay.
Yeah. Did you receive the Wise money?
Yeah. Thank you. Yeah, I received it. So that's working fine, I think.
Okay, that's good. And sorry, I think last time I underpaid you, or I think I've been underpaying you every single time. I didn't know I had to pay an extra $2 for the fee, so I was paying you like $57 instead of $60.
Oh, okay. I did not realize that.
Yeah, sorry about that.
It's fine.
Okay, so I think we're start with question one. So we're on Navy or Stokes now and all that stuff.
Okay.
Where's Muriel here? This one.
Mhm.
So I'm going to start off with listing assumptions.
Mhm.
Um, okay, so these are the assumptions I have. Am I missing anything?
Steady state 2D, incompressible, and gravitational. The assumption as the at the moment 3 4 is like common, and it's way fine. uh, then you can, the thing is that you can write down the equation first. After that, then we can see if some assumption needed to be added or not after that. So at the moment the assumptions are fine as a uh, quite, yeah.
Looking at this, like just the problem itself, is there any way we can tell if it's like Newtonian fluid or not Newtonian fluid?
Yeah, no, usually they consider Newtonian fluid. If it is non-Newtonian fluid, usually they mentioned it. Okay, consider non-Newtonian fluid. You can't tell without looking into it, or given the information, because there is nothing is given about the liquid nature of the liquid. So you can always consider Newtonian fluid.
Okay, so if it's Newtonian fluid, mu is viscosity is constant.
Viscosity does not change with temperature. That also you can consider. Yeah, usually, yeah. Constant properties, basically. Constant properties.
Okay, I'm gonna start off with continuity equation. So because I am considered incompressible, that um, just means this.
Density does not change with.
Yes. So okay. So because it's incompressible, that means nabla u is equal to 0, and nabla is just like x, y, z, or I, j, k. So if you expand that, you get d over dx plus dv over dy plus dw over dz equals to 0. We
Yeah.
are assuming 2D flow.
Hmm.
Um, so now we have d over dx plus dv over dy equals 0. Can we assume that velocity in the x direction is consistent? Like if it like the
Mm,
velocity change with respect to x direction for this example?
velocity change along x direction. Uh, so you said that du dx.
Yeah, I want to know if that's 0 or not, because looking at it, I would probably assume no slip condition, so I would probably say it's 0.
Or no, that you can't say, but you can say fully developed flow. That assumption you can consider.
Okay, so I'm going to assume fully developed flow.
Hmm.
So once it's fully developed, that means velocity is constant, right? So
We fully developed means, develop is like the flow is now the thing is that I'm not sure if you can consider the fully developed condition here, because it's continuously converging, right? It's
yeah.
not straight pipe. So I guess maybe you can't consider the fully developed flow, maybe. Because fully developed is kind of, a flow which has developed, because initially for certain part, like let's say initial length, for some length of the pipe, along that length what will happen is that the flow or the velocity along x-axis will change continuously. But for fully developed flow, the du dx you can consider 0. Now it's a little bit uh, difficult to say whether this is fully developed or not. I guess it's not fully developed, so you can't assume the fully developed flow.
And that's
Yeah.
only because the pipe is changing in shape
I-
continuously, it
I-
seems.
Yes, and also the development, it's called in the flow, in a pipe flow. Usually, it's called development region, or called yeah, entry length. Okay, so entry length means that it's considered some part of the pipe which will take for the flow to be stabilized in terms of the velocity. So that length we don't know unless we know the Reynolds number or the velocity, numerical velocity. So unless it's considered or ask you to consider the assumption, the fully developed flow, you can't take it mostly. Okay. And also you see it's a converging pipe, and also it's not like straight pipe, like a constant area pipe. So I think you can't take the fully developed flow assumption in this case.
Okay, I see. That makes sense. In that case, I don't know what du dx is or dv dy.
Okay. See, you okay. So why you want to use the continuity equation?
Um, I assume we would need it for the linear momentum equations because
But basically, they ask you to particularly calculate some proper like the flow condition, like linear acceleration, rotation, vorticity. So which you just directly you can put the formulas, like the corresponding formulas, and you know the u and v. So it's fine because the velocity components are given, right? The velocity, like the final solution. So the continuity equation you can use when the velocity components are not known, but here you know the velocity component, right? The u and v both. So you don't need to do the the continuity equation in this case, because u and v is already given. Yeah. So because it's the nature of the problem. In this problem, they don't ask you to calculate the velocity because it's already they
given.
calculated it, and they have given the velocity component in terms of x and y both. So in this question, you just have to find the acceleration, rotation, vorticity, and the volumetric strain, and also shear deformation. So it's just you have to put the formulas.
Okay. So equation for linear acceleration,
Hmm.
I guess it's just dv over dt.
Yes, that material derivative dvdt. So which is a little bit low. I think the equation formula itself is quite be long.
Oh,
Yeah, so you will have a acceleration both x axis and y axis. So
yes.
if you yeah, so the formulas are quite big.
So you're saying the formulas are going to be quite big if I start from dv over dt?
No. The formula itself is a little bit big for for acceleration. Big in the sense it's like a you can see it's kind of the same length as the Navier-Stokes equation. Only some parts are not there, but it's I guess the formula in the formula sheet it's there, right?
Yeah.
Yeah, so it will be yeah should be.
I also sent the answer key. if that helps. I didn't look at it yet though.
Okay. I did not. Okay. This is problem, and then yeah. I see. Do you want me to put the the formula?
Yes, please. I don't know what
Yeah.
formula to use.
Yeah, it's fine. So these are the formulas. Yeah. If you see, can you see this? I don't know how to move this one. Yeah, here.
Okay. Oh, yeah, I see
So,
that. Where is
yeah. So,
this derived from? Is this derived from linear momentum?
oh, it's basically a kind of a differential form. It's a differential form. For for example, the acceleration, it's dvdt, right?
Yeah.
Yeah, it's like that. It's not like a derived from momentum equation or fluid equation.
Okay.
It's kind a combination of kinematics and fluid mechanics, because it's the one you wrote du dt. It's called material derivative. So when you expand the material derivative, there will be two component. One is the um, the component due to the time and the space. So basically, this represent, if I mark it, this represent the time change, and this represent the with space. So it's the acceleration with respect how the acceleration changing with time and with space. So it's a combination. So this is called material derivative du dt, which
Yeah.
is from the kinematics part, and then it is just expanded, because you see acceleration, it depends on both sorry, x, y, and t, right?
Yeah.
Yeah, so that's why when you write a basically you can write du dt, right? So now du dt you can expand it such a way, because partial derivative, when you do the partial, you do du dt, which represent the change, acceleration with time, and also this represent, like so basically this is du dt into, you can write it at times du and dx, right? Or you can write this one, right?
Right.
And also dy dt into du dy. You can write this one. So it's from maths. So when you expand it, it would becomes du dt plus u du dx plus v du dy. So if you see the momentum equation, the left hand side of the momentum equation is the same things, right? Because that left hand side of the momentum equation, or if you call the Navier-Stokes equation also, it's that it derived like that way, because that represent the inertia, right? It's Newton second law of motion, that's represent the inertia, which is mass times acceleration. Now when you expand the acceleration, that would be looks like this. So it's from the definitive derivative form to partial derivative form.
Okay, I see.
Yeah.
Mm. So this becomes V, or is this U? So this becomes U?
Yeah, one is yeah, no, the one you marked, it's not you. The left hand side is you. Du dx would be there, because the du dx the velocity, yeah, acceleration. Yeah, the left one is the u. Yeah, that is u, and that is v.
Okay, I see. All right. right, so it just wants us to sub that in then.
Yeah.
Okay. So I would have to do all these derivatives, like this basic.
Yeah, yeah, yeah. I think so. So the DUDT it's zero, so you don't have to do that one, the first part. But the second one you have to do that.
Okay, I think that should be it. Close enough, maybe. I don't
So, oh, so, mm, why did he? Actually it should come little bit smaller. Mm, so you when you did a x u du dx plus a du dy. Okay. Mm, why this one is there? This one, you see?
know. That is from over here. I factored out the u naught, like this side.
Mm. Yeah,
This
that's okay.
squared. I factored out the 1 minus y over y squared to this
Yeah,
side.
that's
So
yeah.
that's why
So
it's
it,
only 1 plus x over L d to the dx,
yeah.
which is
So
this.
that should not be that one, I think. So okay, so u0 x plus l. So when you derivative this part only, it should be only 1 over l, right? Because you are
Right,
derivating with respect to
right.
x.
Hmm.
So it will be 1 over l. So yeah, so it will be 1 over l. Yeah, only 1 over l. Yeah, that part is 1 over l. And then if we go to the, let's see, next one, when you do the with respect to y, uh, so okay, if I see there y with respect to when we will do y, similarly when you do y you can see that d, it's du dy, right? So d, what is u is, why it looks different?
Oh, it's v du dy. So this is the
Yeah,
v, like this stuff here. Oh, so this has to be u still over
yeah.
here.
Yeah, yeah, there should be u, yes, because you see when the acceleration component in x-axis, everything there is u, inside derivative. Similarly for y also, yeah. It's 1 minus y over big Y square, right? Not whole square.
Oh, yeah. Um, just this. Uh-huh. This is factored out, and then I can take out this. And then it's just going to be 1 over
No,
L.
no, 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 you can't take it out. You have to do it, derivative
Oh,
that
it's
part.
dy this time. Yes.
Yeah, it's dy this time, yes.
So then, well, this is a boring question. It's just plug and chug
Y-
formula.
Yes, yes. This question is supposed to be like a little bit tedious kind of work. It's not very, I think. It's
Okay.
just formula. You just put the
I
values.
think then I'm just going to go through what the formulas for rotation, vorticity, if I'm not going to
Yeah.
solve them, and maybe we can do another question.
Yeah, 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 yeah. You can do it by yourself. I think it's just formula. You can put the formulas and you can.
So for the y over big Y, I'm guessing I'm going to take the derivative in terms of the small y.
Hmm. Small y only, yes.
So that's just going to be, yeah, like that. Okay, there. Oh, it's in the wrong place. Okay, that's my final answer.
Mm.
All up here. Okay, so rotation. What would be the formula for that if there's a derivation for it? I'm looking at my formula sheet and I
Okay.
don't seem to have that. I only have R momentum, theta momentum, Z momentum. So I have the two momentum equations as well as a
So,
couple others.
so rotation angular velocity, it's like vorticity equation. So you will see the vorticity like half of dv dx minus du dy, something like that.
Okay. What is vorticity?
Vorticity is kind of it's another name for rotation. Vorticity is kind of whirlpool or something like rotating things. If you can see it in the pond or river or sometimes in the lake, like some tornado shape things.
Oh, okay.
So it's like it's called vortices or so it's coming from that vortices. So vortices is like you can imagine some kind of the things which rotates, and in the center part the pressure is a little bit high, lower, and the outside is pressure is higher. So it's the liquid is kind of in rotation motion. So if I draw it, it would looks like this. So if I draw it here, it looks like let's say like this. And so if I draw like this, so the top side, if you see, it's rotating, it's rotating like this in this direction, let's say one direction. So this is called vortices. And the velocity component of the the angular velocity component, that is called the vorticity. Yeah, angular velocity. So so if you see the formula, it's this one. So yeah, this is the formula for the angular velocity in only z axis, not x and y.
Okay.
Similarly, x and y also the formula would be there.
Okay. How would I find the rate of volumetric strain? That's just dy dx dz, right? Where d is delta.
Mhm. So the volumetric strain, that's the the same formula, but instead of negative minus, it's plus.
Same formula as this.
Yeah, it's just a du dx plus dv dy.
Du dx plus. Oh, so this is the w z, like omega z. That's the formula for vorticity in the z direction because it's going down.
It's basically the angular velocity, but the vorticity is two times of angular velocity. So the vorticity is basically it would be equals to two times of omega z. So that's the vorticity. So
Oh,
it's
so
the
vorticity. And why is
yeah.
it two times that? Is it like,
So that's how it's calculated actually.
oh, and rotation is just this.
Yeah, the rotation
And volumetric strain is the same as this, except instead of minus, it's plus.
plus, yeah.
Why is it plus?
So it's coming from the equation. So the equation, if you see, that is like the how the volume basically it's distorting with respect to time. So when you do the calculation, you put the velocity components, then the things comes as du dx plus dv dy. It's coming from the equation itself, or the definition of volumetric strain. So you see, it's a strain, and that is velocity. Both are different. Strain is basically it's coming from the the stress. Stress is also a kind of related with the pressure, fluid pressure. So when the strain is defined, if you see so if you read then the fluid mechanics, the viscosity part, so you will see the strain is basically defined as like this. You see, you have one a component, and initially let's say the fluid component was like this. Then after applying of stress, it becomes this.
Right.
So there, when you do the calculation, like how the strain is changes. So strain is equals to, you see the distance, this over the initial length. So when you do this calculation, you will find out that the strain is basically dv. So dv dy and du dx, dv dy plus du dx. So remember, this is a little bit different the angular velocity. So if you remember the Newton's, in Newton's law of viscosity, tau is equals to mu into du dy or something like that, right? So here you see the velocity component and corresponding change in the same axis. Like here it is dv dy, not dv dx. Whether in the velocity, the denominator and the numerator, the both, you see the axis and corresponding velocity is opposite. But in this case, strain, it's the same.
Okay.
So you see, it's du dx. But if you see the velocity or vorticity component, it's du dy. So it's opposite, a little bit opposite. Not exactly same, but it's opposite.
Right, because it's dv dy and du dx
Yeah.
instead of dv dx. I see. It's not the same. In that case, for the rate of shear deformation,
Hmm.
um, that just has to do with this, right? Over here.
Which one you?
This over
Ah,
here
yeah, yeah, yeah. This,
has
yeah.
to do with that. Okay. All right. In that case, can we do question 6.79?
Okay.
Wait, is there any way to like add a thing to this, or do we just shift down? I think we just
Ah,
shift down.
yeah. You have to sit down, I think.
Oh, I see. Okay. Incompressible viscous fluids placed between horizontal parallel plates, opposite directions. Oops. For this one, I'm going to assume no slip condition, so velocity of the
Mm,
wall is 0
mm,
over here.
mm.
So can I assume fully developed flow? Because I assume I can because
Yeah,
it's
yeah.
constant.
But you see the boundary condition you chose is not zero. You see the velocities are moving and the plates are moving opposite direction, right?
Oh,
So it should be corresponding that velocity.
so it's not no slip because the plates are moving.
No, no, it's not slip, but it's along with the velocity. So basically, what is no slip condition? No slip condition is the that at the interface of the liquid and the solid, the velocity of the liquid would be the same as the solid, right? So in that case, it was zero because yeah, the plate was stationary. Now in this case, it's not stationary, right?
Right.
So it should be the same velocity as it's moving.
Oh, so okay. That means u at uh
Yeah, the one you wrote, it's correct. U would be equals to U1 and U would be is equals to U2. But it's the sign would be different. U1 is positive, U2 is negative because it's negative x-axis, right?
okay. So this applies for both, like these two
No,
things?
no. You mean the yeah, the direction?
Hmm, wait, or sorry, this should be h. Like this?
Yeah.
U1 at y equals to h equals to 0, and U2 at y equals to 0, because I'm assuming no slip condition.
No, 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 no. No. Okay, again, no sleep condition means what? It's not means it's zero. It does not means it's zero. Okay. So no sleep condition actually tells you that the velocity of the liquid at the interface of between the solid and the liquid would be same as the velocity of the solid body itself, right?
Okay.
So you can imagine like for example, one particle is on the sitting on the solid body. If the solid body is fixed, then the particle velocity will be zero. Now if the solid body moves, that will be the same velocity as the particle also, because particle will move while that. So that is the no slip condition. No slip means there is no slippage of velocity between the liquid and the solid body at the interface.
Okay, so this would be U1, and this is negative U2, is what you were saying.
Yeah.
Okay. Use the Navier-Stokes equations to derive an expression for velocity distribution between the plates. So this time I should start with continuity because we don't know the velocities.
Yeah, yeah, yeah. You can start with.
Okay, so d rho over dt plus rho nabla u equals to 0. We're assuming incompressible flow, so that means du over dx plus dv over dy plus dz or dw over dz equals to 0. I'm going to assume 2d, so z is gone. We assuming no slip, so that means along the x direction, there's no velocity changing, so I can assume this is 0 as well. So that just leaves dv over dy equals to 0. So Navier-Stokes equation, I'm a little bit confused as to like what the full form is. Navier-Stokes equation. Oh, it's just basically Navier-Stokes is essentially linear momentum and linear momentum, but in differential form, correct?
Yes.
Okay. So in the x direction, we're only going to consider x and y, no z. Um, du over dt plus rho d rho u du over dx plus rho v du over dy plus rho w d over dz is to negative dp over dx plus rho gx plus um, plus 2 tau xx over x plus tau xy over x. Okay, no gravity, no time, no z. This is 0. This is 0. Yeah. Um, I don't know about these. The d tau xx, d tau xy. I don't know when to cancel them out and whatnot.
Hmm. Okay, so the Navier-Stokes equation you wrote, it's a good, it's a right form, but the tau is basically substitute with the velocity, because tau is the, you see, it's the strain or the basically stress, and stress is can be written as the velocity form. So you always use the Navier-Stokes equation from the velocity component, with all the velocity component.
Okay, so I'm looking at my notes and they use this special v. They use like this thing. Is that still velocity? What is this? It's like v d squared u over dx squared plus d squared u over dy
Yeah,
squared. Yeah, what is this v?
that v, not v, it's new.
Oh, yeah.
New. It's like it's the viscosity over a density. So it's kinematic viscosity.
Hmm. Okay, so then this becomes mu d squared u over dx squared plus d squared u over dy squared plus d squared u over dz squared. 0, 0. It's just d squared u over dy squared left over.
Okay. Bless you.
Nice. And nu is still here. So what I have left in that case, am I correct to assume everything here is canceled out?
No, no, it's correct. It's correct.
Okay.
Yeah.
Negative dp over dx plus d squared u over dy squared equals to 0. This is what I'm ending up with. And it wants the viscosity, right? So velocity distribution between the plates, that's just u, equals to dp over dx. And do I just isolate for u now?
Hmm. DPD. Okay, pressure gradient you can consider it's a negligible. Okay, pressure gradient you can consider negligible, I think. Otherwise. things will becomes,
Right,
yeah.
because it says the only body force is fluid weight.
Yeah, yeah, yeah.
So do I have to
Ah,
put
they mentioned specially the pressure gradient in x direction is zero. Okay, so they already mentioned that.
in that case, if it said that the fluid weight is the only body force, do I have to replace pressure for like body force or something? Or
Body force means is the rho g. You see the gy is present. So gy is not zero, but is here it's
oh,
gx. So yeah, it's fine.
so is this supposed to be rho gy then over here?
No. Rho gx always x. It's the Navier-Stokes equation in x direction. So it should be rho gx. Yeah, and
Okay,
in x direction there is no g, so it's zero.
right. But when I do the y, I'm gonna have to consider the body force then, or the fluid weight.
Yeah,
So in that case, I'm getting d squared u over dy squared equals to 0.
yeah, yeah,
So
correct.
does that just mean velocity in the x direction is 0?
No. It does not mean zero. It means it could be constant velocity. It does not mean zero. It's
Oh,
just x. Yeah.
so how do I simplify this further? Do I just say u equals to a constant?
No. Oh no. The when you solve it, it would be like so. The first step du dy or du dy would be equals to some constant. Let's say c1. Then the next step u would be c1y plus c2.
Oh, I will integrate it. Okay,
Yeah.
so du over dy equals to c1. And then I'll have to do the boundary conditions.
Hmm.
c1y plus c2. Okay, so I need to know my boundary conditions. So u at y equals to 0 equals to u1 y equals to h equals to negative u2. Um, am I doing my boundary conditions correctly? Because the only difference between u1 and u2 is that the heights are different, as well as like negative u1 and u1.
No. The yeah. So basically, the values are different, right? One is u1, one is u2.
Okay, what else can I add for boundary conditions then?
No, it's correct. You have two boundary condition and two unknown. So you just plug it there.
But this is just u general. Where do I plug in u1 and u2?
So first of all, y is equals to zero. U is equals to u minus u2. So when you said y, okay, you wrote the boundary condition wrong. So I think so. Basically, at y is equals to 0, your velocity is minus u1, and at y is equals to h, your velocity is equals to u2, right?
Okay, if you look at the diagram, I thought this was 0, like the very bottom, because the origin is right here, right?
Yeah, but y is 0, right? Or its
Right.
origin, yeah, y is you see that's the x-axis, right?
Yeah.
So that whole surface represent y is equals to 0.
So this is h, right? But isn't h existing on here and not
Y-
here?
yes.
So then I don't understand why you said for y equals to h, u equals to u2. For y
Ah,
equals
okay, yeah. So it's different. Oh, no. Yeah. You're right. So at y equals to 0, u is equals to minus u2. What I wrote? U equals to minus u2. Ah, okay. It's just x. Yeah. So it will be u2 and this will be u1. Yeah. Yeah, you're right. Yeah.
u2. Okay.
So when you apply this one, you see, if you apply the equation, you will get minus u2 is equals to c2, right? And when you apply the second boundary condition, you will get u1 is equals to C1H plus C2, right? So you know already C2 is minus U2, then C1 would be equals to U1 plus U2 divided by H. So,
So I have du over dy equals to c1.
hmm,
What is equal to du over dy?
d over dy.
Yeah, so I have this, and I have u equals to c1y plus c2.
Hmm.
Mm-hmm.
Yeah. So when you integrating again, because from here to here is the integration again, right?
Yeah,
So that's why C1y plus C2.
yep, that makes sense. And then I just sub in this into here, so that's u
Yeah.
equals to c2.
Yeah.
Okay, and then I sub, what do I use this for?
That you don't need. Why you will use that one? Because you have two boundary condition, and that two boundary condition you can use it in the final equation,
So
right?
then I'm
Because
gonna,
your yeah, because your purpose is here to use the boundary condition to obtain the value of integration constant, right? C1 and C2, because those are unknown.
okay, so I have u equals to c2, now I just need c1, and I sub c2, like u back in. I'm going to get c1y equals to
No, no,
u.
no, no, no. Okay, okay. Okay. Why U is equals to C2? So basically,
Okay,
it's from here, right? U is equals to C1 Y plus C2, right?
yep,
When you apply this one, this condition, so
yep,
Y is 0. So it means U is minus U2, and this is equals to C1 into 0 plus C2. So that's why C2 is equals to minus U2.
okay, so negative u2 equals to c2.
Yeah.
Yeah, and then I sub this c2 back in to find c1.
Yeah.
Minus u2 equals to u. And I'm going to apply the second boundary condition to here now.
Yeah, yeah, yeah.
Okay,
Exactly.
so then this is just c1, oops, c1h, because y equals to h, minus u2 equals to u1. So then c1h equals to u1 plus u2. c1 equals to 1 over h u1 plus u2. Like this.
Yeah.
Okay, okay. So it's 601. So after I find the C1 and the C2, then I would sub that back in. Then I have my equation for U. And then I do
Yeah.
the same thing, but for the Y direction.
Yeah. Y direction? Why Y direction you will do again? You already, if you, once you do it, you will get the value, right? You will get the equation of U.
But don't you have to consider X and Y direction? Or is it just moving in, right? Because
Yeah, yeah. But you don't, you don't need to do the in Y direction, because you already got from the yeah, what do you call the continuity equation, that v is equals to 0, right? There is no velocity in y direction, the velocity component. So the most all of the terms of Navier-Stokes will be 0.
but we also got that du over dx is equal to 0, but we still did everything in the X direction.
Yes, but there itself the v is 0, right? The
Mm.
velocity component is 0. So when you have velocity component, all the terms is 0. And if the velocity is 0, what you will get if you apply the y direction Navier-Stokes equation,
Um,
right? Because you need to find something, and what you will find? Nothing, because v is 0.
okay. But what I don't understand is that U is also 0 for the X
No,
direction.
u is not 0. Who told you u is 0?
Oh, U is constant, is
U
right.
u is only varying in y direction, not in x direction.
U is only varying. Oh, oh, that's what it's saying. It's saying U in the X direction is 0 because it's not varying, but U in the
Yeah.
Y direction is varying.
Yeah.
But for
Because yeah, that's what you got. U is varying in y direction.
Okay, but dv over dy equals to zero is saying that velocity in the y direction is zero. So that's why we don't consider the y direction.
Yeah,
Okay.
yeah, yeah.
Mm. But then we still have the body force in the y direction, the fluid weight that would
Yeah,
exist.
but it does not matter because the velocity itself zero. Then if the velocity is zero, then you don't have anything to calculate, right? The velocity itself zero everywhere. So you will not get anything there. You will get the information of pressure, how pressure is changing in y direction, but nothing with the velocity because velocity is zero.
Mm. Okay. All right, that makes sense. Okay, that's all I have for today then.
Okay.
Yeah. Okay, thank you for your help and sorry for like shifting it so much. I had so much group work last week. It was
Okay. It's fine. It's no worries.
okay.
In terms of group, do you have any like friend or anyone who need tutoring or something like that?
I don't think so. I think I'm the only one that's really struggling.
Uh,
Yeah, it's unfortunately I think my friends are very smart. So, um, is varsity not giving you a lot of clients or anything?
no, actually, the varsity has stopped like contracting UK people. Like if you are like earlier, they had policy like they could hire anywhere from the around the globe, but right now they have stopped contracting the UK
Really?
people.
Because I feel as the UK contributes so many like tutors. Before you, I had another girl who's also from the UK.
Yeah, maybe I don't know. They have stopped from UK. So I saw suddenly that there was no opportunities coming. So I said, what happened? Then I asked them. Then they told me this one, and then I saw in the internet also is yeah they have stopped giving to contracting in the UK people.
Oh, that's unfortunate.
Yeah.
Yeah, that's a shame because you guys, there's so many good tutors from the UK for some reason.
Yeah, there are people I think involved in tutoring. A lot of people here, the teaching as the kind of consider is a, I guess, yeah, a lot of people involved basically. So yeah, so that's why they were involved in the varsity, but they just stopped completely suddenly.
Oh, okay. Yeah, that's all right. I feel as though varsity, there's not many students in engineering that's looking for help there. I feel like it's all high school students, like SAT prep and stuff.
Ah, yes, that's true. I also don't know where basically they use for engineering student. I checked some website was there, but those most of them they need kind of US residents or something like that. Uh,
Oh,
yeah, I don't know anything else. Maybe not much.
that's unfortunate. You could, well, you don't you go to like a university? I'm sure the university will love to hire you because you're like,
Mm.
yeah, you could try that.
It would be, the university thinks it's in person. It's not online, right?
Oh, do you
So
prefer online over in
Uh,
person?
yeah, I prefer online. It's a much more, kind of flexible, right? So
That's
you can
true.
do it. Yeah, you can do it from anywhere, and yeah, it gives the flexibility. Yeah, the in person would be fine, but this gives more flexibility. The online, so that's much better option. And,
Okay, so am I the only one that you're tutoring currently?
I know I have another one, two. I think another one, too. I have, but yeah, they are preparing for some exam. If you are aware of FE and the PE exam, so they are preparing for that.
Oh, the BTEC is what you guys call it, the BTEC exam.
Yes, I think the professional, certification, the FE and PE.
Oh, yeah, no, I don't know
So
that. I only know like A levels and GCSEs.
no, no, no. It's after when you complete your, let's say, engineering. After that, it helps you kind of, for job like a certification. It's in engineering job. It's kind of helps you in terms of promotion or something like that. So a lot of people they apply for this exam, FE, and it's kind of
Oh,
certification.
oh, so they're graduated. They're beyond
Yeah,
me.
yeah, yeah. They graduate.
Yeah, I don't know. The UK does the engineering degree so weirdly because you guys do in 3 years. Well, here it's like 4 to 5 years.
Yeah, okay. I thought it's also 3, 4. Yeah, okay. Yeah, it could be.
It's 3 years, and it's like I'm like, what? So that's so short. No, no way. Okay, all right. Thank you for your help then, Honey Pam. I'll see you next time.
Yeah, yeah, yes, yeah.